Hello everyone, welcome to Brain Blitz Audios. Today, in this episode of NEET Preparation, we'll be looking at previous year questions of physics and medical entrance examinations in India. Today we're dealing with the chapter Magnetism and Matter. This is the 5th chapter in the grade 12 syllabus for physics in CBSE. So let's go on to our first question. The question states, domain formation is the necessary feature of A. Ferromagnetism, B. Diamagnetism, C. Paramagnetism, D. All of these. So what exactly is a domain? We can define a domain as an area in which the magnetic moment of the tiny atoms or magnets, so tiny particles, are arranged in a single direction. So suppose we have a material with domains, maybe we'll have 2 or 3 of them, but the defining characteristic is that all of the atoms or particles present in one domain will point to the same direction. However, 2 or more domains can have different directions. So this is what we call domain. Now, the formation of domains is very important because a material with domains can have a high amount of magnetic attractiveness or repulsiveness when these domains are activated to move in the same direction. So which of the 3 phenomena include domain formation as its necessary feature? Let's look at option B, diamagnetism. In diamagnetism, if we have a diamagnetic material kept in a magnetic field, the magnetic field tends to move around it. So it tends to repel magnetic field because the compounds inside would like to move in the opposite direction. So option B is incorrect. What about option C, paramagnetism? In paramagnetism, there is a slight acceptance of the magnetic field. So the magnetic field is now partially concentrated inside the material, the external magnetic field. But paramagnetic materials are not necessarily the materials which we make as magnets, while the materials which we make as magnets have domain formation in them. So the right answer is option A, ferromagnets. Ferromagnetism is the phenomena in which we need domain formation, because when ferromagnetic materials are kept in a magnetic field, all the domains start to move in the particular direction of the magnetic field. And therefore, one of the domains will start increasing and it will envelop the space occupied by other domains, which makes the susceptibility and permeability of this magnetic material very, very high. So option A is the right option. And since diamagnetism and paramagnetism don't need domain formation, so option D, all of these, is also incorrect. Let's move on to the next question. The best material for the core of a transformer is mild steel, stainless steel, soft iron, hard steel. Now, the core of a transformer needs to perform 2 functions. 1, it should be magnetized quickly, and 2, it must change its polarity quickly. So once if you change the polarity from positive to negative, the material must also change its magnetization direction quickly. So these are the 2 characteristics which characterize the best core. So the property which means that the material is magnetized quickly is permeability. So a material with high permeability will have quickness in magnetization. So if a material has high permeability, it will be magnetized quickly. However, when it comes to magnetic materials and magnets in general, there's something called hysteresis. Now, hysteresis means the lagging behind in terms of magnetic field and magnetic susceptibility. So suppose we have a graph of a magnetic field, then the hysteresis loop of this field must be low in order for the magnetic material to change its polarity quickly. So low hysteresis. If there is high hysteresis, there is a very high difference between the magnetic susceptibility and magnetic permeability. So then it will be harder to change the polarity of this material quickly. So we need to have materials which have low hysteresis as well as high permeability in order to make the core of a transformer. If you look at our options A, B, C, D, all of these are having high permeability. And when it comes to comparisons, steel has more permeability, higher permeability than iron. But there's a catch, and that catch comes in terms of hysteresis. Hard steel, stainless steel, mild steel. All of these kinds of steel have one thing in common. They have high hysteresis. So therefore, it is very hard to change the polarity of stainless steel, mild steel, or hard steel if they're used as the core of a transformer. So therefore, the right answer is option C, soft iron. This has a low amount of hysteresis. So therefore, it is easier to change the polarity of a soft iron solid core of a transformer instead of a steel core for a transformer. And that's why option C is the right option. Let's look at this question. The north pole of a magnet is brought near a metallic ring. Then the direction of the induced current of the ring will be towards north, towards south, anti-clockwise, clockwise. Let's look at our scenario. So we have a metallic ring and a magnet is moved near to it. The north side of the magnet is facing the metallic ring. So when a magnet is moved towards a metallic ring, there is a change in flux. So change in flux produces EMF, which also produces induced current. So in order to find out the current, the induced current's direction, we use the right hand thumb rule. So the flux is moving this way because magnetic field lines are emitted from the North Pole. So the field lines pass through the ring from the North Pole. So let's keep the thumb in the direction of the magnetic field lines. So then the finger curl will now point towards a clockwise rotation, a clockwise movement of induced current. Sounds simple, isn't it? So it means that clockwise should be our answer, but that is wrong because in this particular scenario, we have to apply Lenz's law. So what exactly is Lenz's law? Lenz's law states that the induced electric current flowing in a coil is in the direction such that it opposes the change in flux. So therefore, if the current goes clockwise, then there is no opposition towards the change in magnetic flux. So therefore, since current is induced to go clockwise, then it opposes this induction by moving anti-clockwise. So that is the whole sense of the Lenz's law. So if the magnet is moving towards this coil, then instead of going clockwise, the induced current should go anti-clockwise. And when it goes anti-clockwise like this, then it acts as a north pole. The flux that is produced by the current acts as a north pole, which now opposes the change in magnetic flux brought about by the bar magnet. So therefore, option C is the right option. So the current should go anti-clockwise in order to apply Lenz's law to oppose the change in flux brought about by the north pole of the magnet. Now, clockwise is incorrect because if it was clockwise, if the direction of the induced current was clockwise, then the south pole of the magnet would have come into play. Because when the south pole comes in, the magnetic flux starts to go towards the pole. So therefore, the direction is reversed, so clockwise. Options A and B, toward south and toward north, are incorrect because these represent the pole that is formed by the induced current. So the induced current is trying to resist the change in flux, so therefore it should act as a magnetic pole. So if the north pole is directing in the direction of the coil, then the coil's induced current also forms a north pole in order to oppose the magnetic flux. And when this north pole moves away, then it becomes a south pole in order to respond to the change in magnetic flux. And that's why option C anti-clockwise is the right answer, because here we're asked to find the direction of the induced current, not the polarity of the coil. Next question. The angle of dip is 90 degrees at the equator, middle point, poles, none of these. So we have the Earth, and we need to find out the angle of dip. So field lines of the Earth pass from the north towards the South Pole along its axis. So the Earth is curved up like this. When we reach the equator, we find out that the tangent of this magnetic field is horizontal. So the magnetic field is completely horizontal. So therefore, B cos theta is maximum, which is equal to B. So for B cos theta to be equal to B, cos theta has to be equal to 1. So therefore, theta here is 0 degrees. The angle of dip is equal to 0 degrees. So option A is incorrect. Option B, middle point. Now, if it comes to the equator, then the answer would be 0 degrees. And if you're looking at the actual center of the Earth, then it's not possible. There is no magnetic field lines that are passing through it. So there is no angle of dip there. So option B is incorrect. What about option C, poles? Well, when we reach the poles, now consider this is the North Pole. So over here, the magnetic field is directed vertically inwards. So therefore, the magnetic field is completely vertical. What does this mean? This means that the horizontal component of the magnetic field is 0. The value of B cos theta is also equal to 0. So let's put B to the other side. So cos theta is equal to 0. And this happens when theta is equal to 90 degrees. So theta is 90 degrees when the measurement is taken at the poles. So option C is the right option. The angle of dip is 90 degrees when we're trying to measure it at the poles, north or south. So since we can get angle of dip as 90 degrees at the poles, we can discard option D, which says none of these, so this option D is incorrect because we can find angle of dip as 90 degrees at the poles. Let's look at our next question. What happens when a magnetic substance is heated? Now, before we move on, let's look at what happens inside a magnetic substance. So, magnetic substance is a substance which, under a magnetic field, atoms are arranged in uniform order due to the magnetic field. So when we pass a magnetic field through a magnetic substance, we find that the atoms or constituent particles, they are in a uniform order, which is why ferromagnetic materials are very good at being magnetic substances because their domains become in uniform order. So this is due to the external magnetic field. What happens when the magnetic substance is heated? When any substance is heated, then the particles, the constituent particles, they gain energy. So when they gain energy, their direction now becomes more random. They want to go off from side to side or in any random direction in order to release that pent-up energy. So therefore, the very existence of magnetism in that magnetic substance is now null and void. So therefore, when a magnetic substance is heated, it loses its magnetism. So therefore, option A is the right option. Option B is incorrect because if it becomes a strong magnet, then the atoms arranged in uniform order has to be more in that material, which is not when a magnetic substance is heated. Does not affect magnetism is incorrect because magnetism is dependent on the uniform order of the constituent particles, which when heated is getting lost. And either B and C is also incorrect because both of these statements are wrong. So the right answer is option A. When a magnetic substance is heated, it loses its magnetism due to the fact that in a magnetic substance, atoms are arranged in uniform order due to the external magnetic field. However, when this gets heated, the particles inside the magnetic substance, they gain energy, and when they gain energy, their direction becomes more random. So therefore, there is no uniform direction, so the magnetic substance loses its magnetism. Let's look at our final question. We have a magnet 10 centimeters long, and it has a pole strength of 2 ampere meters. And this is deflected through an angle 30 degrees from the magnetic meridian. The horizontal component of the Earth's induction is 0.32 into 10 raised to minus 4 Tesla. We need to find the value of deflecting couple. So let's write down our quantities first. 10 centimeters. And when it comes to the length of a magnet, we're looking at a quantity known as magnetic length. So therefore, this is equal to 2L. So 2L is equal to 10 centimeters, which we can write as 10 raised to minus 1 meters. And next, pole strength, represented by small m, is given as 2 ampere meter. Then what we're given is the angle of deflection, phi. So let's take phi as 30 degrees as given in our question. Then the horizontal component of the Earth's induction. So the Earth's magnetic field horizontal component, which is represented by BH, is 0.32 into 10 raised to minus 4 Tesla. So we have our quantities. Now we need to find the value of the deflecting couple. Remember that couple is just another word for the quantity torque. So we need to find the torque that this magnet is experiencing. What is the formula for torque? Torque in magnetic terms is equal to mb sine theta. It is the cross product of magnetic moment of the magnet and the external magnetic field. However, notice that we're not given the magnetic moment. That is easily remedied by using the formula magnetic moment is equal to pole strength times the magnetic length. So let's plug in our values. Pole strength is 2 times 2L is equal to 0.1. So we have a magnetic moment of 0.2. Okay, so let's come back to torque. So we now know the magnetic moment, which is 0.2 times the magnetic field, which in this case is the horizontal component, and then sine of theta, or the angle, which now becomes sine of phi, or sine 30 degrees. 0.2, let's write it as 2 into 10 raised to minus 1. Now this is due to an important reason, which we'll see as we calculate. BH, the horizontal component of the magnetic field, can be written as 0.32 into 10 raised to minus 4 times sine 30 is 1 by 2. And since we made 0.2 as 2 into 10 raised to minus 1, we're now free to eliminate the 2 from the numerator and the denominator. So now we get 0.32 into 10 raised to minus 5. And the unit for torque is Newton meters, Nm. Now, this answer is correct. However, if you look at our options, you find that none of the options are given in decimals. So now what we do, we need to convert this from a decimal into a whole number. So here it's 0.32. We can convert this as 32 times 10 raised to minus 5 minus 2. So that's 10 raised to minus 7 Newton meters. And which of the options contain 32 times 10 raised to minus 7 Newton meters? It is option A. Option A, 32 times 10 raised to minus 7 Newton meters is the right answer. And we use the formula torque is equal to mb sine theta. This is known as a cross product. When it comes to all the other options, we find that 16 is just half of the value, so it's incorrect. 64 is twice the value, which is incorrect. And 48 is 4 by 3 times the value, which is incorrect. The right answer is option A, 32 times 10 raised to minus 7 Newton meters. Again, using calculation and finding out the answer using the formula torque is equal to mb sine theta and finding the magnetic moment by using pole strength times the magnetic length. And that concludes this episode of NEET preparation. Remember, we have a lot of episodes on NEET preparation. Don't forget to click on the playlist and its link given in the description down below to enjoy more of our videos. And also, if you want to get more of our useful and interesting content, don't forget to subscribe to our channel, Brain Blitz Audios. We'll be back with more useful content such as learner words, mind maps, NEET preparation in excess, and also other important playlists such as memory hacks, etc. So until the next webisode, take care, stay safe, bye-bye for now.